Welcome to the fifth unit of week number 3 in the OpenHBI course Parallel Programming Concepts. We meanwhile discussed different ways of dealing with concurrency and parallel activities in a shared memory world. So at the end of this week we want to have a look into more elaborated research ideas of how to deal with shared memory parallelism. When we look into the given programming models we have in the shared memory world, one of the main issues there is concurrency as a first-class citizen. So we take different ways of expressing concurrency in our languages, such as threads or tasks, and then try to synchronize the access to the shared memory variables by the means of, for example, mutexes or semaphores. The interesting point here is that whenever we deal with shared memory or shared information, global variables in our different activities, we always need to answer the question about the so-called memory model. So the question is a particular value visible if it's changed? We already had the example of OpenMP, which has a relaxed consistency model. So it may happen in OpenMP code that if you write a value, that another task reading the value shortly after can't see the latest written value. This could be reasoned, for example, by caching effect, where the write attempt only goes to the cache, but the value in main memory is not updated so far. If you have such a condition where you need to consider the memory model, then you need according support in your language and in your runtime library to have a predictable behavior. So all the different languages, such as C# or Java or C++11, that promise direct support for concurrency as part of the language, also need to talk about their memory model. They need to tell you, okay, what happens if you write to variables to shared memory from different activities, from different tasks and threads? When is the stuff visible? What kind of synchronization primitives, such as flush, can I use in order to make sure that all see the same value? And you need the specification in order to be sure that in your code there are no hidden race conditions. When you take now this situation, then this could be declared as state-of-the-art. So in the current world of parallel programming concepts and models, we have a more or less well understood idea of memory models and language support. And the interesting question now is this enough? Is this all we need in order to deal with parallelization and parallel programming on modern systems? And if you remember the first week where we spent a lot of time talking about hardware, then we introduced there a concept called non-uniform memory architecture, NUMA. And the NUMA concept was the idea that we have different kinds of sockets or processors, and each of the processors has local cores, and the cores have a calling cache, and each of these processors also have an attached piece of memory. So we distribute the physical memory, the memory hardware, over the whole system and attach it to different processors. Whenever an activity, a thread, for example, on one of the processors tries to access a memory address that lies in a physical memory bank located at another processor, some kind of chip interconnect has to be used in order to access this value. This leads to the fact that the access time to main memory may differ. So you may have fast accesses to your own local memory that is directly attached to your physical processor, or you may have a little bit longer time for the access to memory when your read attempt or write attempt has to travel over the processor interconnect network to another memory module. If you now take this approach and think for a moment about the chip interconnect being a real network connection, then you can have a situation where you have even large-scale NUMA systems, for example, in high-performance computing world, where some activities access memory by reading and writing the values that may take, where the operation may take a little bit longer than the access to your own local memory. This was the non-uniform memory architecture idea in parallel hardware. And the question is now, is this considered in the programming languages? And if you remember now what you have seen in the different task and thread-based approaches, there was no real notion of how long it takes to actually access a value. The only interesting question was, how can we synchronize the access, how can we avoid race conditions, and how can we express a particular level of parallelism inside our solution? The whole situation of having a lack of support for NUMA hardware, for NUMA parallel hardware in the languages led to the development of a new research field. And this research field covers the idea of so-called PGAS languages. PGAS stands for Partitioned Global Address Space. So we have a global address space that is accessible from all the threads or tasks, but this address space is now partitioned. There's a partition that is local for one of the threads, while another partition is remote for this thread. So from the viewpoint of each of the threads or the tasks, you have the idea of local memory that is fast to access and remote memory that is far away. When we move this concept to the programming language, so when we make this explicit for the programmer, this allows to have better optimizations for the particular situation. So a programmer that is aware of the fact that some memory is faster than the other may now design the program in a way that frequently accessed data items are only kept in local memory, while not so frequently accessed items are kept in another part of memory. So PGAS languages basically add another concept into the programming language world, into the shared memory programming language world, where they say we add an idea of local and global or local and remote memory access inside of our language. There are different PGAS languages under development. As I said, all of this is research work, so we are not aware of any commercial products using one of these languages. So please take this mainly as an interesting look into the future. Examples for such PGAS languages being used, especially in scientific high-performance computing, are Unified Parallel C or Co-Array Fortran. Sun also started a development for a language called Fortress. We have ideas for Java with Titanium, and we have one particular language we want to talk about today, which is X10 by IBM. The core management functionalities for dealing with the NUMA hardware are typically abstracted in a library. So we have a language extension or even a new programming language which can deal with NUMA aspects, which can have a notion of local and remote memory. But then under the hood, you need some kind of synchronization of data access. You need to deal with all these resources. And as you can see on the slide, there's a couple of libraries already abstracting this away. Most of them deal with shared nothing environments, hardware environments that give you the transparent notion of a virtual shared memory system. So we see that later in week number 5. So let's talk about X10 in order to see one example for a PGAS languages in order to grasp how they want to exploit the NUMA capabilities of the underlying hardware. So X10 is a parallel object-oriented language. It's developed by IBM Research and it's derived from Java, similar to Scala. The language in itself, the X10 language, compiles into C++ or Java code, which allows you then to use stable and product versioned compilers for Java or C++ code. So at the end you have a very stable compilation framework as long as the translation from X10 code to Java or C++ works. You have then binaries that can interact based on the X10 runtime library, even in a shared nothing environment, and you have support for different processor architectures and also operating systems as a runtime environment. X10 in itself has the fork join execution model we already know from OpenMP. So a main thread, a main activity is able to spawn different tasks. These tasks then perform the concurrent activities and may run in parallel. And at the end, all of these tasks are synchronized again by an implicit or explicit barrier in order to continue with a serial execution stream. The new notion of NUMA in X10 is expressed by the concept of places. So one application instance, running application, is executed on the number of places, and each of these places represents a NUMA node. Places can be detected and queried as part of the code, so you can ask how many places are there, on how many places do I run, and then you can start to optimize your data access based on the place where you run. The main method, so the starting point for your X10 application, automatically runs at place number 0, and each of the places automatically gets a static copy, a private copy of static variables. So variables that do not change can already be copied to the different nodes. Here's an example for how this works in practice. So you have your different NUMA places, and as we know from the parallel hardware lecture, NUMA places may be either processors in a single computer system, in a single desktop system, or it may be even a shared memory, shared nothing system where you have a NUMA programming model on top of it. You define parallel tasks, and each of the tasks lives on one of the places. A direct variable access is only allowed in your local place. So whenever you want to access a remote variable, you have to make this explicitly as a separate language construct. The direct working with variables is only possible if you rely on your local variables. The implementation strategy, how that maps to real operating systems, depends on the runtime environment. So X10 is flexible in this way. The implementation strategy today is that you have one operating system process per place, and each of these processes then manages a number of threads in order to map the tasks that run at this place to the particular threads running on this processor. The first relevant keyword in X10 is the async keyword. It allows you to create a new task that executes a particular code block. The async call returns immediately because the activity in the code block is spawned as a separate task that can run concurrently. And this piece of code you refer to with your async keyword then may reference all the variables in the enclosing block. So you just say, I have a piece of code and it's somehow self-contained. I can run it on a place with all its local variables. And then the runtime chooses the right place for this piece of code. It may check the load conditions, see which of the different places has no activities at the moment, or where more operating system resources are free. So you as a developer are completely decoupled from these decisions. The runtime is doing this for you. The second main keyword, similar to what we have seen before, is finish, which allows you to execute a code block but then wait for all the transitively spawned threads and tasks. So this is similar to what we saw with the Silk synchronization primitives. So here's a code example. We see that we have a Fibonacci class, which is again intended to compute the Fibonacci number. And here we use finish and async in order to implement our recursive call. So the async call in the brackets is performed as separate tasks, so it returns immediately. And the surrounding finish statement makes sure that the overall block is only finalized when all the asynchronous calls that are recursively spawned are finished. So when the finish block terminates, we have the final two numbers to be added together in order to get our result. Another point you need, again, in order to work with shared memory programming is the atomic statement. So atomic allows you to define a critical section in your code. You can have a piece of a code block, a piece of code that runs only once in relation to the other activities. And this only works if this code block accesses local data, because otherwise you would run into potential race conditions and critical sections in your code. A more elaborated version of this is the guarded expression. So you can use the when statement to suspend a task until a particular condition holds, and then you can execute your statement in an atomic way. You may remember that this somehow is similar to what we have seen with condition variables and synchronized blocks in other languages. So hopefully you meanwhile see that a lot of these concepts we discuss here repeat again and again in different variations in the different languages. Here's a code example on the left side for the atomic statement, where we say we want to have a bank account class, and there we have a transfer method, and this transfer method hopefully performs an atomic operation which is only run by one of the concurrent activities. The other is the guard expression in the right example, where we have a send and receive primitive, and where we relate to the existence of a particular condition before we actually run the code in an atomic way. Beside the default concurrency support that you find also in all the other languages, X10 now has elaborated support for working with the different places, and this is mainly implemented in the add statement. Add S allows you here, as written in the example, to execute a statement at a particular place and to block the current task until this activity is done. So this is a kind of a manual scheduling where you say, I'm pretty sure that I need another place in order to execute this, and I know that the local data on this place is given, so please run it there where I have the data available. Another variation of this is the add statement with an expression. So you can also say you want to run an expression, maybe a complex one, compute-intensive one, on another place, again with the idea of putting the work to the place where the data lives. So the best way to deal with NUMA systems is to not move data around where you need it, but to actually move the work to the place where the data is already living. And since we have the notion of local and remote data in X10, it is natural to now find a way to move your activities, your tasks, to the node where the data lives. So in a typical X10 program, you would distribute your data over the different places, and then you would start to spawn out different tasks and put them on the places where the actual data lives. This is far more efficient than moving huge data blocks around, and it gives you very nice capabilities of dealing with the underlying NUMA infrastructure. And by this, I want to finalize the week number 3 about programming models, parallel programming models in the shared memory world. We did a very quick rush through a set of concepts in shared memory programming. We know that this is not complete and not exhaustive, but the idea here was to show you that a couple of basic concepts, for example, synchronization, critical section implementation, the idea of task parallelism, can be found in the different languages and libraries. So the basic takeaway from this week is that we have 3 major ways of dealing with parallelism in the shared memory world. The first one is the process model, where we define multiple processes in an explicit piece of shared memory. We didn't talk about this too deeply because this is only helpful if you have extremely coarse-grained parallelism with only a few synchronization attempts. The second way of dealing with parallelism in the shared memory world is multi-threading. So you use the operating system concept of threads in order to formulate multiple parallel activities, and then the operating system scheduler is putting your threads on cores and processors, on processing elements, in order to run them in parallel. This is what we know as this classic approach for parallelization in the shared memory world. But meanwhile, we have an even more flexible approach with the task parallel programming. So in the task model, you use, for example, OpenMP or other approaches to define fine-grained concurrent pieces of work in your code, and then you let a runtime library or a runtime system decide how to map these tasks on a given number of threads. The threads are not explicitly created by yourself, but they are created by the runtime system in accordance to what is available as a number of cores, a number of processors in the system. This allows you to create a more portable piece of code, a more portable piece of parallel code, and should be treated as the default meanwhile in parallel programming in the shared memory world. We saw different examples, not only in native code, C, C++, but also in managed code such as Java or C#. And if you want to get even further and want to have a more high-level abstraction from the particular parallel hardware, then we come to functional programming, as it can be seen in Scala or in other languages, where you just express pieces of functionality and you hand this over to a higher order function. And this higher order function, for example, then filters your given values based on the provided input function. And this can be then parallelized by the runtime library automatically without having any kind of task or thread definition inside your code. So functional programming is the ultimate abstraction in order to get parallelization in your code. It leads to something that we call implicit parallelism. So you just write down your functionality. You no longer express any kind of concurrency in your code, and all the work is done by the runtime library. What we see in practice is typically a healthy mixture of all these approaches. So people start to use languages that have functional parts, object-oriented parts, classical concurrency support, and mix and match all of this together in order to get a piece of code that hopefully uses the given parallel hardware resources in the most efficient way. The last thing we talked about in this week was a little outlook into what is going on in research. And in research, we have the idea of partitioned global address space programming languages, where the notion of NUMA hardware is visible in the programming language, so you can write your code in a way that it works with memory of different latencies in the shared memory system. And by this, I want to finalize the week number 3. Next week, Frank Feinbubel will tell you all the details about accelerator-based programming and how that helps you with the speed up of your code by doing some kind of good parallelization.